All right, problem 4. The nerves that supply sensation to the front portion of a person's foot run between the long bones of the foot. Tight-fitting shoes can squeeze these nerves between the bones, causing pain when the nerves swell. This condition is called Morton's neuroma. Because most people have a dominant foot, muscular development is not the same in both feet. People who have Morton's neuroma may have the condition in only one foot, or they may have it in both feet. Investigators selected a random sample of 12 adult females with Morton's neuroma to study this disease further. The data below are measurements of nerve swelling as recorded by a physician. A value of 1 is considered normal and 2 is considered extreme swelling. So basically normal is 1, and up to 2 is extreme, and then we have the in-betweens. The population distribution of the swelling measurements is approximately normal for adult females who have Morton's neuroma. Nice of them to tell us that. All right, so we have this long table. For right now, we're not going to use it. We will come back to it because it's going to be necessary, but right now, not necessary. A scatter plot of the ordered pairs of the swelling in the left foot and the swelling in the right foot is shown below. All right, so basically, right foot, left foot, and the scatter plot suggests that there are 2 distinct groups of patients. Patients within each group share a common trait. Use the scatter plot above and the table on page 10, or the pay table above, to determine the common trait and explain how this trait differs for the 2 groups. Well, right here, what I notice is, hey, these people apparently have a right foot that's swell. These people have a left foot that's swell. And the question is, well, great. Why? Well, as it turns out, when I look at the table, I go, you know what? All the people that have the problem in their left foot, that's their dominant foot. And so their dominant foot swells more because the foot with neuroma is left. It's my dominant foot. And look, swelling in the dominant is larger than in the non-dominant, all the way down, as long as I'm working with left foot, being left foot dominant. When I go to right foot dominant, I notice that the right foot swells more. So basically there's more swelling in the left foot when that's the dominant foot, and there's more swelling in the right foot when that's the dominant foot. So the trait that distinguishes the patient group is the dominant foot. The dominant foot is more swollen than the other foot. Patients whose left foot is more swollen are left foot dominant, and those patients that are whose right foot is more swollen are right foot dominant. And that's a little bit confusing, so I'm going to pause to ask for questions. Okay, so when I was modifying this problem, I wanted to create a 2-sample T. All right, and then when I actually went about answering it, I realized there was a problem. So I do want to talk about it. So those people who are watching this video later, you don't need to copy the part in yellow, but I do want to provide that for some instruction purposes. So determine whether or not the mean level of swelling in the left foot is different than that of the right foot. Great. So I could sit there and I basically reorganized the table. And I said, all right, I put all the left foot swelling in one column, and basically I had to pull that information from the original table, and you can copy it down there and look and try to figure it out in a moment. But so all the left foot swelling in this column and all the right foot swelling in this column. And notice sometimes the left foot swollen more, sometimes the right foot is swollen more. But they're all ordered together. I was like, hey, I'm going to compare the left foot to the right foot. So I went ahead and said mean 1 equals mean 2. And I want to see if there's a difference, so mean 1 does not equal mean 2. And I defined it. And then I got to my conditions. And the very first condition is 2 independent random samples. And guess what? These are not independent random samples. And here's why. That's the left and right foot of patient 1. Consequently, they're very related. because it's all measured from the same patient. So the same patient was measured twice, so that makes this a paired t-test. So even though I was hoping to set up a problem where I was going to run a 2-sample, it wasn't, because I didn't meet this condition because the data was paired. So I was like, well, you know what? I'm going to go ahead and run it as a paired test the way I should, even though that's wasn't what my intent was. So if it's a paired, mean difference is 0, and then the mean difference does not equal 0. And I said the true population mean difference from left minus right. And you could have done right minus left, it wouldn't have mattered. I just chose left minus right because I had left column first. All right, condition, random sample of 12. They told us that in the previous problem. N needs to be less than 12%. I mean, less than 10%, and we had 12, so 12 divided by 0.1 is 120. There are more than 120 women with neuroma, or Morton's neuroma. Part 3, it's reasonable to assume that the test differences between the women are independent. Not always required, varies from year to year whether you should include that, but it's never wrong not to. It's never wrong to include it, so I'm including it here. All right, so I took the data, and I have a whole lot of data that's going to appear on the screen because I didn't want to slow things down. So I have all the data in L1 and all the data in L2. So this table here in red that I made is in L1 and L2. And then I went to the top of L3, and I'm going to go ahead and clear that out. And I went second 1 for the left foot minus second 2 for the right foot. And then it populated all my data. So now I have the differences. Then I need to check to see if it's normal enough, whether there's too much skewness or not. So first stat plot's on. I choose the one with outliers, press enter. My X list is in L3. Zoom 9, and I get a pretty symmetric box plot. If I were going to say anything about it, I might say that it has a larger IQR because the tails on the IQR is a little wider. But in general, this is pretty symmetric. That's good. So the box plot is reasonably symmetric with no outliers. The distribution appears to be approximately normal. And just as a reminder, I can use the trace feature to actually get my minimum, my Q1, my median, my Q3, and my max. So I can use the trace feature followed by the arrows to get those values, which is all I used. I didn't make a real scale. All right. This is my formula. The X bar minus mu standard deviation divided by the square root of n. Please use the D's. So basically, it's the same as a regular T statistic. Because if it were a t-test, you'd write T equals X bar minus mu S divided by the square root of n. But in this case, because it's for the difference, just add some D's in there. If you don't, I don't think they're going to count off for it, but it's better to have it. All right. So where did I get these values? I went ahead and ran the test. To get these values, I went ahead and ran the test, then I plugged in. So stats, test, this is a t-test. I made sure data is highlighted because I'm using data. My mean claim came from here, it's 0. And my data happens to be listed in L3, so second 3. I'm looking to see if there was no difference, so this needs to be a not equal. And it turns out I get a t-statistic of 0.3, a p-value of 0.8223. Here's my X bar, negative, 0.0208. I guess it shouldn't have been negative. And standard deviation of 0.3137. So these values right here, I just pulled off the calculator and plugged in. All right. So my p-value, oh, by the way, when you get your z-score, I had to multiply by 2. And the reason I had to multiply 2 times that probability is because this was a 2-sample t. If you leave the 2 off, they're probably not going to ding you for it. But once again, because this was a not 2-sample, because this was not equal, I needed to be multiplying by 2. It probably won't ding you if you don't write it, but it's more correct to have it. Okay, so 0.8223 is larger than any reasonable alpha. We're going to fail to reject the null. So our p-value is 0.8223. We failed to reject the null. There is not sufficient evidence at alpha equal 0.05 to suggest the true population mean difference in foot swelling, left minus right, is different than 0. It does not appear that the left and right foot have a difference in mean swelling. And that sort of makes sense when I just look at the table, because here I have some of the left feet swelling more. Then over here I have some of the right feet swelling more. So they probably are going to average out, because sometimes the left foot swells more, sometimes the right foot swells more. And we already said, based on a scatter plot, that depended on the dominant foot. All right, that depended on the dominant foot. And because of that, I'm going to ask the next question. What would be a better test than the one selected in part 4 and part B? Well, a better test would be to measure the swelling in the dominant foot versus the non-dominant. This is because, based on the scatter plot, we could identify this trait separated the women into 2 groups. So it wasn't the left foot and right foot that determined, because sometimes left foot was swelling more, sometimes right foot was swelling more. And that happened dependent on whether it was a dominant foot. Because what we determined was the dominant foot always swelled more. Okay, so I know y'all are all excited because we have more scatter plots. And basically this is the one that was on the first page, but this is a new one. All right, so this was the one that was on the first page. This is a new one. So scatter plot of the ordered pair swelling in the dominant foot, swelling in the is shown below. What can that swelling in non-dominant, swelling in the dominant foot is your X versus swelling in the non-dominant. And I know this because they put this in parentheses in this in the comma. So they basically gave me this paired data, and that's what we have here. Swelling in the dominant, swelling in the non-dominant. What conclusion can be drawn from the scatter plot that's not apparent from the scatter plot in part A? Well, this was part A. So this is one in part A, and this is the one that we have now. Well, what I noticed real quickly is here I have 2 distinct groups. But when I look at this, and they didn't ask me about A, they said, what is different about this one, or what can I see here that I can't see in part A? And I sit there and go, oh, I see a trend. I see that for every patient, I see in general, not for every patient, but in general, as the swelling increases in the in the dominant foot, swelling also increases in the non-dominant foot. So the scatter plot part in scatter plot in part D indicates that swelling in the non-dominant foot increases as swelling increases in the dominant foot. So it just basically says, hey, I can sit there and see that as this one increases, as the X's increases, the Y's generally increase as well. I'm not 100% sure that's the case here, because I don't know if this person is associated with that person. I have no idea what the association is over there, but here I definitely know the association. So that's what I can pick up. Give just a moment while people copy that down, so I'll pause for just a moment. Moving on to the next part. Can we conclude that there's a difference between the mean swelling in the dominant and the mean swelling in the non-dominant for adult females who have Morton's neuroma and at least 1 foot? Give statistical justification to support your answer. So before we compared left foot to right foot, and we said that there is no difference, but now we're going to compare the dominant foot swelling versus the non-dominant. So once again, because this is a patient being measured twice, when something is measured twice or they're naturally paired, That makes it a paired test. So we're going to mu D equals 0, and mu D does not equal 0. And we're basically, the only thing we wrote differently on our definition, instead of being left minus right, it's dominant minus non-dominant. And this is completely different because here our right foot is our dominant. And if you noticed, all these values are larger than the non-dominant. Okay, all of them. All the dominants are larger than the non-dominant. So there definitely is some sort of distinction there. How much, we don't know yet. So random sample, 12 given. N is less than 10%. There are more than 120 women with neuroma. Reasonable to assume that those differences are independent. We address that. So I need to input all this data into either L1 or L2. I'm going to tell you that because I wanted to speed things up when I did this. I have this in L4 and this in L5, just so that I could have both sets of data in my calculator. So I have that data input in L4 and L5. I'm going to go to the top of L6, second L4 minus second L5. So it's dominant minus non-dominant. That populates it. Then I'm going to go to my stat plot. Oops. There we go. Make sure it's on. It is. Now, my X list is in L6. Y'all's is probably going to be in L3, but mine's now in L6 where I did the subtraction. So second 6, zoom 9. And I see a little bit of skewness, but it's not too bad. Once again, I can use the trace feature to get the median, the Q1, the minimum, etc. So I can use a trace feature along with the arrows. But when I do that, I end up getting a box plot that looks something like this, which reasonably symmetric with no outliers. And if you want to, you can use a phrase, no extreme skewness and no outliers. Distribution appears normal enough or approximately normal. Once I have that, T equals X bar minus mu, S divided by the square root of N, drop some D's on it. These values I'm going to get when I actually run the test, so I'm going to go ahead and take a moment and run it. Stat test. Once again, this is a t-test. I have data. We said that the null hypothesis claim was 0. My data list is in L6. Yours may be in L3 or somewhere else, but mine's in L6. So second 6. We're looking for not equal. And I get a huge t-statistic of 10.68. And then I have a very small p-value, 0.0006 zeros, followed by a 3. That's approximately 0. Anyway, my X bar happens to be 2.875. Obviously a typo. 0.2875 minus 0, then 0.0932. And the probability of getting that Z statistic is approximately 0. The p-value is 0, that's less than any alpha. So we're going to reject the null, and our p-value is approximately 0. There is sufficient evidence at alpha equal 0.05 to suggest the true population mean difference in foot swelling, dominant minus non-dominant. Please always say what you're subtracting. This makes life better for you and better for the grader. Is different than 0. I use the phrase is different because in my alternative hypothesis, I had not equal. All right. Finally, it appears that the dominant foot swells more. That's my my conclusion. All right, in simplified terms. Pausing recording. Offline, and I'm just going to go back and say this. I said that this was the two problems I'm given today. I think are more difficult than what would happen on Friday of next week, but these are not excessively difficult, so it could happen. So I want you to be prepared for these. The other thing I wanted to say is I would be really surprised if they had you input data on Friday of next week, but it could happen. So that's why let's review it real quickly. But I sort of suspect that they won't. I suspect that they're going to give you summarized data to work with. All right. Last part. The nerve swelling measurements is used to indicate whether a foot has Morton's neuroma. Use the 24 measurements of nerve swelling to suggest a criterion for diagnosing Morton's neuroma. Justify your suggestion graphically. All right, you could have used a number of different graphs. I don't know why. I thought it'd be fun to do something with a stem and leaf plot. So here's what I did. I have my group without neuroma, the foot without, this should say foot without neuroma, and foot with neuroma. Well, if you notice, there's a lot more feet with neuroma than without, and that's because when I look at the data table, we have left foot. Well, if they have the left foot, that means they don't in the right, but some of them had it in both feet. And because of the both feet, I end up with more on the with neuroma side. So basically, if it has a left, then I'm going to have a value. If it has a right, then I'm going to have a value. But if it's not, I'll have, if it's left, I mean, if it's, but otherwise I won't have values without neuroma. If I have both, they're going to be all on the neuroma side. So I went and listed the values, and you can sit there and go, okay, they only had it in one foot. In their non-dominant foot, the swelling was 1.10. Well, that non-dominant doesn't have neuroma, so 1.10 is right here. When I come over to here for this left foot, I end up with 1.40, and that's with neuroma, and that's the swelling. So basically, that's the way I chose to break it up. I could have done it a different way, but that's the way I thought to make a nice, easy way to compare. And they said, based on this, is there a way that I could make a criterion for diagnosing Morton's neuroma? And when I'm sitting there looking at this, the one thing I noticed is no one with neuroma has less than a 1.4. No one without neuroma has greater than a 1.4. So this part should have been highlighted in red. But based on the stem plot below, it appears that one could use a swelling rate of 1 to diagnose neuroma. And basically, I should say, if it's greater than 1.4, they have neuroma. So if it's about 1.4 or greater, it appears they have neuroma. If the swelling is greater than or equal to 1.4, it appears that the patient has neuroma. And I know it's Morton's neuroma, but I'm trying to keep it brief. Oops, not what I want to do, resume share. I should have said this earlier, but if you always need to have a scale, so I have one, 1.7/3 is a swelling rate of 1.73. Please make sure that you give a legend or a key, I should say. They will deduct points, all right? And make sure you have labels. Really important.